In section 9a, we defined a function. In this section, we are looking at a specific function, which is the linear function. And we've come across this before, I'm sure, in an algebra class. That is a straight line function. And we'll see how real world situations can be modeled using the straight line function. Now, you all recall the equation of a straight line function, which is y equals mx plus b. So m is called the slope of the function, and that's a very important fact that we need to know about a straight line. Now, in a real world situation, the slope is also called the rate of change, because if you remember the definition of slope, it is the change in y over the change in x. This we learned in algebra. Now, that is the same as saying the change in the dependent variable over the change in the independent variable. So it's the rate of change of the dependent variable per 1 unit of the independent variable. And that's the reason why slope is called the rate of change. Let's look at the first problem. We're given two different relationships between x and y, and we're going to try to graph it on the paper. So this is our first. So let's call that line 1. And the second, we're going to call it line 2, because if you graph it, you'll see that it's just a straight line. Now, we use a scale, a convenient scale, so we can actually see these two lines well. And you'll see that line 1 is steeper than line 2. The height of the points in line 1 increase much faster than the height of points in line 2. Just compare these two. So the line 1 always sits above line 2. So these are the observations that we make when we actually graph the functions. So knowing the definition of slope or rate of change, you can see that the rate of change of y with respect to x in line 1 is greater than the rate of change of y with respect to x in line 2. So slope of line 1 is greater than slope of line 2. And how do we figure out the slope? It's rise over run or change in y over change in x. So we just draw a little triangle here to figure out how x and y change. So if you're looking at y, it would be the vertical distance. So the change in y is 2, where the change in x is 1 unit. So change in y over change in x for line 1 is 2 over 1. That's the slope of line 1. Again, we draw a triangle. Notice that this is 1. So that's why we have a 1 here. And the change in y is also 1 unit, because we're comparing it to this. So that's 1 unit. So the slope of the second line is equal to 1 over 1, which is 1. So the slope of line 1 is greater than slope of line 2, and we know exactly what the slopes are. And from the graph, this is exactly what we gathered. Change in y over change in x is 2 over 1 for line 1. For 2 units, or for 1 unit increase in x, y increases by 2 units. So an increase is always positive, and that's why you see these positive signs. So the slope is positive. A rising line always has positive slope. And in the second line, clearly 1 over 1 is equal to 1. So change in y is an increase in y by 1 unit. Increase in x is also 1 unit. So as x increases by 1 unit, y increases by 1 unit. So that's how we figure out the slope. So increase is always given by a positive sign. So the slope is also positive, obviously, because the numerator and denominator are positive. Both are rising lines, but the slope of line 1 is 2, which is greater than slope of line 2. So that tells us the line 1 is steeper than line 2. Now, we know that the rate of change is the slope, which is the change in the dependent variable divided by the change in the independent variable. So if we multiply both sides by the independent variable, and that's what we've done here. So the independent variable and cancels with the independent variable on the right, and the independent variable gets multiplied to the slope on the left. So basically the change in the dependent variable, since these two got cancelled, it's by itself now, is equal to the independent variable times the slope. So this relationship is nothing new. It's just the same equation, which is the equation of the rate of change, written in a different way, just by using simple algebra. So knowing the rate of change, suppose we know the rate of change and we know the change in the independent variable, we can figure out the change in the dependent variable. Out of these three, if we know any one, we can, or any two, we can figure out the third one. So read the question carefully, and if you notice that one of these three is missing, that is either rate of change or change in the independent variable or the change in the dependent variable, while the other two are given to you, then all you have to do is plug in the numbers and figure out the unknown using simple algebra. So let's read the question. It says you drive along the highway at a constant speed of 65 miles per hour. How far do you travel in 3.5 hours or in 6.8 hours? So the rate is 65 miles per hour. The minute you see per hour, it is the rate. If you see a change in a certain variable divided by change in another variable, then that can be called the rate. The numerator is the dependent variable. The denominator is the change in the independent variable. Now, how far do you travel in 3.5 hours? So the change in the independent variable, that is time, is 3.5 hours. We are asked to find the change in the dependent variable, which is the distance traveled. So what is the change in your distance when the change in time is 3.5 hours? You know the rate, write down the equation, you know the rate, you know the change in the independent variable, plug in the numbers, and you get the change in the dependent variable is 227.5 miles. So that is the same as saying that in 3.5 hours, we can travel 227.5 miles, given that we're traveling at a rate of 65 miles per 1 hour. So similarly, let's assume that the rate is exactly the same as before. Now the time, we're answering the second question here. The time is 6.8 hours. That is the change in the independent variable. And the question says, what is the change in the dependent variable, which means how far will this, how far would you have traveled in 6.8 hours? So we use the exact same formula. Change in the dependent variable is equal to the rate of change times the change in the independent variable. So we plug in the numbers and get 442 miles, which means that in 6.8 hours, the distance traveled is 442 miles. Now, the second question, or the next question, that is question number 3, the gas station owner finds that for every penny, so there's a 1 cent increase in the price of gasoline, she sells 120 fewer gallons of gas per week. So as gas price increases, people buy fewer gallons. So that's the relationship that we see here. So she sells 120 fewer gallons. So just remember that's 120 fewer gallons in a week. So what are the variables here? The two variables are um, gas price and um, the amount of gas sold. So the number of gallons sold depends on gas price. So number of gallons sold depends on gas price. So gas price is the independent variable. Number of gallons sold is the dependent variable. The change in gas price, which is the change in the independent variable, is equal to 1 cent. It's positive 1 cent because it's an increase. So increase is always denoted by positive, an increase of 1 cent. The change in the dependent variable is the number of gallons sold is a decrease of 120 gallons. So a decrease is always denoted by a negative sign. So notice that the change in the gas price, the change in X is positive. The change in the number of gallons sold is negative. The question says, how much more or less gas will she sell if she raises the price by 10 cents per gallon? So first, let's figure out the rate of change of the dependent variable with respect to the independent variable. So first, we're trying to figure out the rate based on the information that's given. The change in the number of gallons sold, that is the change in the dependent variable, divided by the change in the independent variable. So we divide one by the other, and we get negative 120 gallons per 1 cent of increase. So for every 1 cent change, there is 1 cent increase. Now, the question that we need to answer is how much more or less gas will she sell if she raises the price by 10 cents? So what is the change in the number of gallons sold, which is the change in the dependent variable, when we know that the change in the independent variable, which is the gas price, is an increase of 10 cents, which is positive 10 cents. And we just figured out the rate of change of the amount of gas sold with respect to the change in price of gas. So plugging in the numbers into the equation, rate times change in the independent variable is equal to the change in the dependent variable, which we're trying to figure out. Plug in the numbers, so negative 120 times 10, so I'm just simply plugging in the numbers I have, is negative 1200 gallons, since the dependent variable, change in the dependent variable, the units would be gallons because the dependent variable is the amount of gas sold. So how do we interpret this negative? Negative is a decrease. 1,200 fewer gallons, so there is a negative explained here. Fewer gallons will be sold per week for a 10-cent increase in gas price. Before we discuss the general equation, let's continue with the second part of the same question that we were discussing. The change in the dependent variable is the number of gallons. Dependent variable is the number of gallons. We don't know what it is. When the change in gas price, which is the change in the independent variable, which is gas price, is negative 5 cents. It's a decrease of 5 cents, so it's negative 5 cents. So change in the dependent variable, which is the number of gallons of gas, is equal to slope times change in the independent variable, which is the gas price. So slope, which is the rate of change, is negative 120 gallons per 1 cent times negative 5, which is the decrease in gas price, is equal to 600 gallons. And then the answer is positive because the negative and negative get cancelled. So the change in the dependent variable, which is the number of gallons, is equal to 600 gallons, which means for a 5-cent decrease in the price of gas per gallon, 600 gallons more will be sold per week. So more gas, and how much more? 600 gallons more will be sold in a week for a 5-cent decrease in gas prices.